Hey there, Algebra 2 students, and welcome back to Miss McGuire's classroom. Today, we get to start talking about an Algebra 2 subject, so we're kind of pressing pause on the Algebra 1 review, and we're going to be talking about domain, range, and end behavior of graphs. So remember, as you take your notes, that you're writing down all of the examples. If I write it down, you write it down on your paper as well, and let's go ahead and get to work. Don't forget your first and last name, period, and date in the top right hand corner of your notes as well. So this is Unit 1, Lesson 6. And our topic today is, this is basically going to be an introduction to you about domain, range, and end behavior. The objective for today is I will be able to analyze and describe key parts of graphs, including key terms such as domain, range, and end behavior. So I will be able to analyze and describe key features of graphs using key terms such as domain, range, and end behavior. All right, so the first thing we need to talk about today is domain. What exactly is domain? Well, domain is basically a description of all of your x values. So it's all of your x values. And what else do we know that we can call x values? If we have a function, we know that we can call an x value our inputs. And the domain basically describes everything that x can be for that function or for that graph. So it describes all the values that x can be, what you're allowed to use on that graph, what x values you can use for that function or that relation. So then what's your range? Well, if domain is focused on your x values and your inputs, then range must be focused on your y values, also known as our outputs. So range focuses on your outputs or your y values. So your range is basically a description of everything that y can be, everything that you're allowed to plug in for y, or everything you're allowed to get out of your function for your outputs. So it's a description of what y. All right, let's go ahead and talk about our end behavior then. So end behavior is another way to describe the graph. It's a way to describe the graph's behavior, or what the graph does to the far left and the far right. So it describes the far left and far right portions of a graph. So today you're going to learn how to describe a graph by describing what its domain is, its range, as well as its end behavior. So let me show you some examples. So for example 1, as you can see, we have 6 different graphs here. And for all 6 of these graphs, we are going to identify the domain, the range, and the end behavior of the graph. So there's a couple things that we need to do to each of these graphs though. And for those of you who are doing this on notebook paper, you do need to sketch each of these graphs into your notes. Your sketches don't have to be perfect. You don't need like the exact points, like every single point. Just make sure you get the key points correct in your notes and make a decent sketch. So for example 1, we actually need to add some arrows to this graph. So I'm going to add arrows to the axes. I also need to label my axes, X and Y. And then we're going to add arrows to the graph itself. So that way we can see that this graph continues on infinitely to the left and to the right. Okay, so now that we've added some key labels and some arrows, now we can get to talking about this graph in particular. So this graph, as you can see, is a parabola that faces upward. So it's an upward facing parabola. So this parabola uses all of the x values to the left and to the right. For example, because this parabola extends off to the left, we know that it's going to extend to the left forever, which means that all of these x values, these negative x values, are part of our domain. So when I describe domain range, we're going to use our interval notation, just like we did with our inequalities. So for interval notation, you describe what happens to the left and to the right, and then you use parentheses or brackets. So to the left, I'm headed in the negative infinity direction. And then to the right, I'm headed in the positive infinity direction. So my domain is negative infinity to positive infinity. Because this graph also extends to the right forever. As this would extend, it'll continue to like grow out, and like go farther up to the right, of course. And you'll see like that you can plug in all of these x values into that function, and they will be given outputs and be a part of this graph. Now let's talk about the range, sorry. Let's talk about the range. So for the range, remember we're describing the y values. So in this case, well, here's 0 on the y-axis, right? And the y-axis goes up and down instead of left and right. But if you actually took the paper and rotated it, you would see that the negative y values go off to the left and the positive y values go off to the right. So we can still talk about it in terms of left to right. But what we need to notice about this parabola in particular is that all of the y values on this graph are above 0, which means that this graph does not go below 0 on the y-axis. So our range actually starts at 0. And we include 0 because there is a closed circle at 0, 0. All right, at the origin. Then all of these y values then, so all the y values continue to go up, and all these y values continue to go up in the positive y direction, which means that we will extend to infinity for this graph. So for this graph, the range is 0 to infinity. Then what about the end behavior? So this is what should be new for you guys, is describing the end behavior of a graph. So remember that we said that the definition of end behavior is that it describes the far left and far right portions of a graph. So to do that, we're going to discuss what happens to the left of the graph and then to the right of the graph. So for this particular graph, and actually for all graphs, the way that you're going to describe this is you're always going to say as x approaches negative infinity, comma, y approaches, and then you're going to tell me what y approaches. So as you can see, as x approaches negative infinity, so as our x's go off in the negative direction, what are the y's doing? Well, the y's, as the x's go to the left, the y's continue to rise, which means that we're headed in the positive infinity direction, which I don't need that positive sign in front. We can just say infinity. and know that it's positive infinity. So as x approaches negative infinity, y approaches positive infinity. And I just want to make a note to myself that that's what those arrows mean. Those arrows mean the word approaches. So as x approaches negative infinity, y approaches positive infinity. So we just described what's happening on the left side of this graph. Now we need to describe what happens on the right side of this graph. So for the right side, you're going to say as x approaches, well, to the right of this graph, x is approaching positive infinity. And what's y doing as x approaches positive infinity? Well, as you can see, as the x values increase, so do the y values, which means as x goes to positive infinity, y also approaches positive infinity. Let's do this one more time with this graph here. So for this graph, we're going to go ahead and add our arrows and our x and y labels for the axes. All right, so let's talk about this domain. So what is the domain of this graph? Well, because this graph extends to the left and it's extending forever, we know that our x's are extending as well forever. So to the left, we go to negative infinity. And then what happens to the right? Well, to the right, again, this graph extends forever, and it's going to stretch and open up more and more and more as it increases, as x increases. So we know that we're headed towards the positive infinity side for our domain. Now we need to talk about the y values. So for the y values, I see that my y values don't go lower than this line right here. All the y values are above it. That means that y can't be less than whatever number this is right here. Well, I believe that number is halfway between 0 and negative 1, so this should be negative 0.5. So if all the y's are greater than negative 0.5, that means that negative 0.5 is the least y can be, and the greatest it can be is positive infinity, because our graph is going up or forward in that positive y direction forever. So now let's talk about our end behavior. So for our end behavior, we're going to describe as x approaches negative infinity, y approaches, and then as x approaches positive infinity, y approaches. So let's fill that in. So what does y approach as x approaches negative infinity? Well, as x approaches negative infinity, as x goes from 0 to negative 1 to negative 2 and so on, y is increasing. So y is going towards positive infinity. Well, what happens as x approaches positive infinity? Well, as x starts from 0 and increases to 1, 2, 3, 4, all those numbers, what's y doing? Y is also increasing. So y still goes to positive infinity. Now let's do another example together before you try some on your own. So again, for this graph, we're just going to add some quick arrows to our axes so we know that they extend forever, and to our graph as well, so we know that it extends forever. So let's go ahead and talk about our domain and our range. So for our domain, it looks like x goes from 0 to negative 2 and then carries on. So those x values are going to continue decreasing in that negative infinity direction. So we start with negative infinity. And then our domain, or our x values, increase from 0 to all these positive numbers on the right side. So we go to positive infinity. All right, what about our range? So if you check out our range, it looks like all of the y values, they like hit 3. We're going to call it 3. It's a little bit above 3, but we're just going to call it 3 for simplicity's sake. And then all the y values are actually below that. All of these y values are below that value of 3. So that, if if everything's below 3, sorry, that means that 3 would be the highest number, or the biggest that y could be. So that's actually our right-hand side here. So 3 is as big as it can be. And then what's the smallest or the least value y can be? Well, our graph extends down forever in the negative direction, so the least would be negative infinity. So our our range is negative infinity to 3. So to set up our end behavior answer here, we're going to say as x approaches negative infinity, y approaches whatever. And as x approaches positive infinity, y approaches whatever. So let's see if we can figure out what y approaches for each of these. Well, as x, as x approaches negative infinity, so x is 0 here, and then it gets to -1, -2, and so on, y increases at first, but then to the far left, it actually starts to decrease. And according to this arrow, it's going to decrease forever. So as x approaches negative infinity, as it gets smaller and smaller, y approaches negative infinity as well. Then what about as x approaches positive infinity? Well, at first, as x gets bigger, y does too, but then from there it turns and it starts going down, and then it decreases forever. So as x approaches positive infinity, y approaches negative infinity once again. So why don't you go ahead and try to describe the domain, the range, and the end behavior of this graph on your own. Let's quickly get these arrows and the labels we need. Sketch that graph real quick and then answer some questions about it. So let's check your answers compared to mine. So for the domain of this graph, I noticed that for my domain, when x starts at 0 and then decreases to -1, and then it's headed towards -2, -3, etc. So we start with a negative infinity as our left bound. And then for the right boundary, it looks like as my x is increasing forever. So I go to positive infinity. Hey, I caught a typo before I published the video. How nice. It's positive infinity. I did that for my y's too. My range. All right. Then for my range, it looks like my y's extend downward forever, so they head towards negative infinity, and then my y's extend up forever, or towards positive infinity. So my range is negative infinity to positive infinity. Then my end behavior, so to the far left, as my x decreases, so does the y. So as x approaches negative infinity, y approaches negative infinity as well. Then going to the far right, those x's approach positive infinity, and so do the y's. So what I have is as x approaches positive infinity, y approaches positive infinity as well. Now let's do another example on your own. So what am I saying? Sketch this graph real quick, and then you are going to answer some questions about it. So make sure you add those arrows to the axes and to the graph itself, and label your x and y axes. So go ahead and find the domain, range, and end behavior of this graph on your own. So go ahead and check your answer against mine. I got for my domain that x includes the values of negative infinity to positive infinity. For my range, y also includes negative infinity to positive infinity. For the end behavior, as x approaches negative infinity, y also approaches negative infinity. The y values decrease in that direction. As x approaches positive infinity, the y values increase, and approach positive infinity as well. Here we have a linear function, or a straight line, as our final example. So I would like you to find the domain, range, and end behavior of the graph of this line as well. So this graph actually has its arrows. It looks like the picture got cut off a little bit for the x-axis, but you can see it extends to the right, it extends to the left. So go ahead and tell me the domain, range, and end behavior of this graph. So for this graph, I got that the domain is negative infinity to positive infinity. The range is the same. And as for the end behavior, as x approaches negative infinity, as those x's decrease, y approaches negative infinity as well. Then, to the far right, as x approaches positive infinity, y approaches positive infinity as well. For this next example, we are going to graph an equation by using a table of values. So we're going to plug in some inputs, find some outputs, and then graph those points to help us graph the entire equation. When we're done, we're going to describe the domain, the range, and the end behavior, just like we've been doing. So our equation is a function. We have f of x is equal to x plus 1. So to graph using a table of values, we're going to pick a bunch of inputs, plug them in for x, and get our outputs. So I'm going to plug in -3, -2, -1, 0, 1, 2, and 3. And the reason why I like these numbers is because it gives me a nice selection of some negatives, 0, and some positives as well. So let's plug in -3. So f of -3 is equal to -3 plus 1, which is -2. F of -2 would be -2 plus 1, which is -1. F of -1 is equal to -1 plus 1, which is 0. F of 0 is 0 plus 1, which is 1. F of 1 is 1 plus 1, which is 2. F of 2 is 2 plus 1, which is 3. And f of 3 is 3 plus 1, which is 4. So as you can see, we have a nice array of points here. So a table of values is the same thing as a list of points. So this table of values, this -3, -2, is really the point -3, -2. -2, -1 is really -2, -1 as a coordinate point. We're going to plot those points. But before you do that, there's some things you need to know about graphing in this class. Anytime you make a graph for this class, you have to have the following clearly labeled to get full points. So what I need you to label on your graph is, first of all, you need to label your axes, x and y. Then you need to label your scale. And when you do that, you need to put dashes at every single point here. And trust me, when you do this, it makes your graph easier to read, it makes it more legible, and the point is I want you to be able to hand your graph to a random person on the street, and that random person on the street should be able to read your graph clearly without you having to explain it to them. So now you need to label at least every other number on your scale. So for this scale, we're going to count by ones, and I'm going to label all the evens. So the first one would be 1, then we would have 2, 3, 4, 5, 6. I can zoom in for you right now. Then on the other side, the middle, the origin, is 0, 0. That's your origin. So 0, 1, 2, 3, 4, 5, 6, etc. On the left side of that origin then would be -1, -2, -3, -4, -5, -6. Then for the y-axis, above 0, or if you simply turned your paper to the right of 0, would be 1, 2, 3, 4, 5, 6. So then the other side of the y-axis would be the negatives. So this is what your graph has to have in order for you to get credit for your homework, for a quiz, or a test. If your graph isn't labeled like this, you will automatically get a 0. I need to be able to read your graphs. I'm the random person on the street who needs to be able to read your graph without an explanation. So this clearly labels your graph and lets me know exactly what's going on. So to get credit for a graph, you have to have your x and y axes labeled, you have to have your dashes, and you have to have at least every other number on your scale labeled. All right, let's go ahead and start graphing these coordinate points. So our first point is -3, -2. So I'm going to go to -3 on the x-axis, -2 on the y, -2, -1, -1, 0, 0, 1, 1, 2, 2, 3, and 3, 4. And then that's enough points to get an idea of what this graph looks like. And then you're going to draw a line that goes through all of those points and extends all the way across your graph. So make sure your line extends all the way across your graph. If your line is this long, you're not going to get full credit. You need to show me exactly what this behavior of this graph is. And to do that, you need to show me how the graph extends across the entire coordinate plane. All right, so now we're going to describe the domain, range, and end behavior of this graph. So the domain of this graph. Now, are there any numbers we aren't allowed to plug in for x? Could we have plugged in negative fractions? Could we have plugged in negative decimals, positive fractions? Could we have plugged in positive 1,000, negative 1,000? Yes, there's nothing x can't be. In fact, our graph shows that. It shows that to the far right, x extends forever. To the far left, x extends forever. I think I switched those directions there. You know what I mean. So for our domain, x can be all the negative numbers and all the positive numbers. So our domain goes from negative infinity to positive infinity. Then our range does the same because it extends to the left forever and to the right forever. Our range is negative infinity to positive infinity. And for our end behavior, we're going to write as x approaches positive infinity, y approaches whatever, and then as x approaches negative, sorry, that should have been negative infinity first, positive infinity second, y approaches whatever. So what's happening as x approaches negative infinity? As x approaches negative infinity, y is decreasing. So y approaches negative infinity as well. There's a negative right there. Then as x approaches positive infinity, so as this graph extends off to the right forever, y is increasing. So y also extends to positive infinity, or approaches, sorry, positive infinity. So now why don't you go ahead and give an example a shot on your own. So for your example, you're going to let the function be equal to x squared minus 4. So f of x equals x squared minus 4. You're going to use a table of values to help you plot the graph and then connect your graphs with either a line or a curve depending on the shape that this particular graph takes. I recommend that you still use -3, +3. Plug those numbers into your function, get your outputs, and then plot your points on your coordinate plane. Don't forget to label your graph the way that you're supposed to in order to get full credit for graphs in your Algebra 2 class. Then discuss your domain, range, and end behavior. And I'll give you some time to work on that on your own, and then you can check your work when you're done. The first thing we want to check is your table of values. So these are the f of x's, or the outputs that I got for all of my inputs. Then I clearly labeled my graph. I have my x and my y axes labeled. I have all my dashes, and then I have my scale labeled. I counted by ones, which you can clearly see, and I labeled every other one. Then I plotted my points, and then I drew my curve in and realized that I had a parabola. So the domain of this function is negative infinity to positive infinity. My x's will extend to the right forever. My x's will extend to the left forever. So it includes all real numbers. Then for the range, well, I noticed that there aren't any y values below -4. So that tells me that -4 is the least y can be, and it extends forever above that. So my range includes -4 to infinity. Then for my end behavior, as x approaches negative infinity, y approaches positive infinity. So as x approaches negative infinity off to the left, my y's increase. Then to the right, as x approaches positive infinity this time, the y's also approach positive infinity. So that's my domain, range, and end behavior. That's all for today's notes. Now you may get started on your homework. I'll see you back in class in just a little bit.